Ask My Instructor 9.4.21. Use the divergence test to determine whether the following series diverges or state that the test is inconclusive. So, what is the divergence test? The divergence test says that if a series converges, then the terms go to zero. Equivalently, if the terms do not go to zero, then you know the series diverges. One thing I want you to pay attention to is that the divergence test only tells you if the series diverges. It does not have the power to tell you that a series converges. So knowing that the terms go to zero is not enough for convergence. If the terms go to zero, all you know is that the divergence test is inconclusive. The series may converge, but it may not. You just don't know. For example, the harmonic series diverges even though the terms of the series approach zero. So the divergence test will not tell you if the series converges. However, it is a quick and easy way to check for divergence. And I like to do a quick divergence test anytime I'm analyzing a series for convergence. So what I do, if I have a series that I'm trying to analyze, is I just do a quick divergence test. If the terms go to zero, then I know I have more work to do. But if I see that the terms don't go to zero, then bammo, I'm done. And by and large, the divergence test is the easiest. Now I'm going to take a little bit longer to do the problem that we have, but that's only because I'm trying to give you some background information that I hope will help you. All right, so with our problem, we have the ratio of two functions, and so I'm going to use the growth rate theorem. So maybe you don't know the growth rate theorem. The growth rate theorem is basically an ordering of sequences that I'm about to give you in just a minute. And with that ordering of sequences, if A comes before B, then the ratio of A over B, that ratio will go to zero. And if A comes before B, then B over A is infinity. So that's the technical definition. A more loosey-goosey idea is that if A appears before B in the list, then A grows more slowly than B. And so here's my list. I've got my logarithm functions first. My log functions grow the slowest. And then after that is a polynomial. Polynomials are the next. And then after that is some combination of polynomial and logs, like a product. And that's, if the powers are right. And then another polynomial. So roughly speaking, it's log and then polynomial and then exponential. Do you see the b to the n? That's your exponential. Then exponential, and then factorial, and then n to the n. So the left-hand side grows the slowest, and then as you move from left to right, you've got functions that have faster and faster growth rates, and so that n to the n has your fastest growth. And so by looking at this, I know that an exponential function grows faster than a polynomial function, and an exponential sequence will grow faster than a polynomial sequence. And in the same way, a factorial sequence is going to grow faster than an exponential sequence. Now keep in mind, we're talking about growth rate, not who is bigger for a particular value of n. So it is not until n equals 25 that the factorial sequence is greater than the exponential sequence. So it has to do with growth rate. Who is bigger in the long run? Our two functions, we have a log function and and then a polynomial function. It's actually a monomial because there's only one term. Now the monomial, 9 times radical n, that's on the top, and on the bottom is the logarithmic function. So we have a numerator that's growing faster than the denominator, meaning that if the numerator grows faster than the denominator, then the ratio is going to infinity by the growth rate theorem. And in particular, the limit is non-zero. And so by the divergence test, we conclude that the series diverges. Take care. Have fun with this. Bye.